One major thing topologists concern themselves with is whether or not two topological spaces are, in some sense, equivalent. If you've taken any abstract algebra courses, you might think I'm talking about some type of isomorphism between topological spaces. And that's the correct way to think about it, although isomorphisms really only exist between algebraic objects like groups, rings, fields, etc. But there's a corresponding idea with topological spaces. And so a lot of the times, instead of talking about the topological spaces themselves, what topologists do is talk about functions on those spaces. And a function on a topological space is usually thought of as some type of deformation of that space. Okay, so you might be thinking about a space as the surface of a sphere or the surface of a donut or some arbitrary manifold or Euclidean space or whatever. And we know that if you're thinking of linear algebra, then you can talk about linear deformations of Euclidean space, like skewing, stretching, rotating, stuff like that, rigid kind of deformations. But topologists concern themselves with more fluid deformations. Really, it's anything that's a continuous function. Okay, so continuity, as defined in an analysis course, would tell you that a function is continuous if whenever 2 points in your domain start out close together, they end up close together, right? So a small change in the distance between your points in your domain results in a small change in the distance in the codomain. Topologists have an alternative, but surprisingly equivalent definition. If you haven't seen the proof that this definition is equivalent to the epsilon delta definition, I highly recommend looking it up. But the definition for topologists is that a function is continuous if the preimage of every open set is open. Preimage of open is open. That's all continuous means. And then this is written as, well, yeah, your open sets in your codomain, call them U prime. The preimage of that is in the topology on your domain, right? So that means the preimage is open. Very beautiful definition, typically very easy to work with. And it turns out that if you know a lot about the continuous maps on a space, you actually know a lot about the space itself. So sometimes it's easier to study maps on a space rather than the space itself. And if you want to talk about two different spaces, or at least two spaces that look different, but you're not sure if they're actually fundamentally different in a topological sense, what you want to talk about are homeomorphisms. Not homomorphisms, which are from your abstract algebra course, but homeomorphisms, which imply that your function is bijective, meaning it has an inverse. It's continuous in the sense that the preimage of every open set is open, and its inverse is also continuous. So it's continuous in both directions. Sometimes people call that bicontinuous. And of course, it has to be bijective for that inverse to even exist. Okay, so homeomorphisms let you detect topological differences between two spaces. Why? Well, there are a ton of proofs, a ton of theorems that state that homeomorphisms preserve really important topological concepts. We haven't seen many topological concepts yet, but I'll just rattle some off. If you start with a space that's connected, so X is some blob with no divisions in it, it's not two blobs, it's one blob, then a homeomorphism may do a lot of weird stuff to it, but it will ensure it's still a single blob, that it's still connected in the codomain. And I guess I'll call this f of x. The image stays connected. Cool. So homeomorphisms preserve connectedness. They also preserve something called compactness. So compactness in your analysis course means closed and bounded. So you might as well imagine, R2, you have some closed and bounded set, A, and if you apply some function f to it, and if that function is a homeomorphism, again, it may do some weird things. It may actually, maybe it doesn't have any corners anymore, and maybe it's really big on one side, but it'll still be compact. It'll still be closed and bounded. And homeomorphisms preserve the number of holes that an object has. So if you were to say, take a donut and deform it by a homeomorphism, then again, it may end up looking weird, but it'll still only have one hole in it. 3D. And a lot of other things. So homeomorphisms preserve topological properties. They are exactly the topological equivalent of an isomorphism, where isomorphism preserved the group structure or the ring structure or whatever. Homeomorphisms preserve the topological structure. And so they're really nice to work with. What are some examples of continuous functions and homeomorphisms? Well, the identity map is always continuous, and that should be fairly obvious according to our definition of continuity. The identity map sends every point to itself. So in particular, if I start with an open set, the preimage of that set will be itself. So it'll still be open. Right? Preimage of open is open. Similarly, inclusion maps are going to be continuous. So if I started with, maybe I'll be general and make it like half open, half closed kind of thing, some subspace Y of X. And I think of the inclusion map taking Y into X, which means you just send every point to itself, but you're only really talking about points in Y. Then that map is continuous because, okay, again, for any open set I take, say I took some open set in Y, let's make sure it's open everywhere. So that's my open set V, maybe call it, or U prime or whatever. Yeah, I think I used U prime previously. Then the preimage of U prime is itself. But I'm allowed to take any open set in X, right? My codomain is X, so I could have taken, this open set. What's the preimage of that? Well, the preimage would be the part of it contained in Y, and that's at least relatively open. Right, so I called Y a subspace, meaning the open sets are those that are relatively open in Y. So in this case, yes, the preimage of that open set is an open set in Y. So the identity inclusion maps are continuous. It's also useful to know that if you start with a continuous map, here I'll just build on our notion of continuity and Euclidean space. So here's some nice continuous function f defined on some portion of the real line. I don't really care which. And I could think about restricting it. Maybe I restrict it to this closed interval. Then what happens? Well, the restriction looks like that. I mean, really, it should overlay perfectly, but I'm just drawing it slightly off center so it makes some kind of sense. I'll say that's F restricted to A, where A is this red set. And of course, the restriction there is going to be continuous. Right, again, you could think about the pre-image of any open set, and sure enough, it will be open. Okay, what else do we have? Compositions of continuous maps are continuous, similar to real analysis. But what if we take some weird topologies? So if I took the discrete topology on my domain, and I won't even tell you what the topology is on my codomain, it won't matter. No matter what y is, all functions are continuous if your domain is discretized. Why is that the case? Well, remember, discrete means all sets are open. So no matter what, say I have some u prime and y, no matter what function f I take, the pre-image of u is automatically open, because the pre-image is some subset of x. And every subset of x is open by the definition of the discrete topology. So weirdly, the discrete topology makes every function continuous, whereas the indiscrete topology, if you put it on the codomain, does the exact same thing. So if the codomain only has two open sets, right? Remember, indiscrete topology means tau prime, the only open sets are the empty set in the whole space. In this case, our space is y. Then yeah, all I have to check is that the pre-image of those are open. But the pre-image of, again, it doesn't matter what the function is, the pre-image of the empty set is going to be the empty set. And the pre-image of the entire codomain is going to be the domain. Cool. That works for any function. So yeah, the pre-image of the empty set is empty. Pre-image of open is open. Pre-image of the whole space is the whole space. And by the definition of topology, the whole space is open. So there you go. Every function to the indiscrete topology is continuous. But who cares, right? We're not talking about weird examples like that usually. Usually we want to talk about nice things. So intuitively, what does continuous mean? Intuitively, it means you're not tearing the space. And again, that should kind of agree with your knowledge of real analysis, in the sense that, if you had some function and I introduce some tear right here, some like discontinuity, right? I'm talking about it as tearing that otherwise nice curve apart, then that's not continuous. In topology, we like to draw shapes though, rather than typical functions. So instead, we think of a function as a deformation of space. Right? So the function f might take this circle and deform it ever so slightly in this kind of bendy circle. Now, what's true of that? Well, that is a continuous function. And it's also going to be a homeomorphism. Right? I mean, I haven't written what the function is, but hopefully you believe me in that it's continuous in the sense that if I were to start with 2 points, say those 2 points that are close together in the domain, they'll be close together in the codomain. And no matter where I shift them, if they start out close together, they'll end up close together. And somehow that's equivalent to pre-image of open being open. Similarly, you might define some open sliver of that, and it would map to this open sliver. Right? So pre-image of open is open. And it's a homeomorphism because I can go in reverse. Right? This is apparently a nice bijective map, and it's all smooth and everything, so we should be good. What about the function g? Well, the function g is actually continuous. Right here, I'm turning it into a figure 8. And it's continuous in the sense that, yeah, pick 2 points close together, they'll map close together. Cool. Even if I picked, these 2 points on either side of the blue dot, presumably those map to like here, say. Because all I'm doing is like, you can think about this function as like gradually deforming and bringing that in until you do get a nice figure 8. I don't know if I drew that very well, but oops. Anyway, hopefully you get the idea. It's a nice continuous motion. But I mean, the way I've written it or the way I've drawn it, you don't really have bijectivity at all, to be honest. So you can't really talk about an inverse function. For example, if you think about these 2 antipodal points, this one over here, and this one right here, they sort of map to the same point, right? I'm squishing them together. And so it's not injective. So I can't really talk about a homeomorphism. So I won't even write homeomorphism, I'll just say bijective, no. Maybe I will write homeomorphism. And what about something like this? Something like the map H. What I'm thinking of happening with H is right here, right, that half will map to this half. And then the rest of it comes here. So I'm kind of tearing the space. I'm grabbing it by the bead on the bracelet and ripping it apart, flattening the bracelet out. Well, that function H, I mean, as I say up here, continuous maps don't tear the space. That would not be a continuous map. Why not? Again, you can say, well, points that start out close together, in this case, maybe I'll draw them in different colors. Let's do yellow and red. Well, red would map to this side, yellow would map to this side. So they started out close together in the domain, ended up really far apart in the codomain. So that's a tear. It's a sort of discontinuity you've introduced. So H would not be a continuous map. It's an inverse function if you wanted to define it, which you can. I mean, this is a bijective map, or you can make it into a bijective map depending on how you define this sort of interval here. Its inverse could be thought of as continuous in the sense that if you started with 2 points close together on the line, they would end up close together on the circle. But since it's not, since H going the forward direction is not continuous, it's not going to be a homeomorphism. Okay, so this is what I meant when I said homeomorphisms preserve topological properties. One thing you'll notice about the circle is it has a hole. Well, it's homeomorphic to this, which also has a hole. It's not homeomorphic to this, which has 2 holes. It's not homeomorphic to this, which has no holes, right? So homeomorphisms preserve the number of holes in your topological object, and they preserve lots of other things as well. But this example, I wanted to really stress the holes argument. So down here I say, intuitively homeomorphisms preserve or perform neither tearing nor gluing, right? So this one was not a homeomorphism because it failed to be bijective. And it failed to be bijective because it sort of glued these two ends together. And this one failed to be a homeomorphism because it tore the circle apart into a flat line. So in general, that's sort of how topologists think of homeomorphisms. Nice, continuous transformations that don't tear or glue any part of the space. That's why people will make the joke from time to time that a coffee cup, so let me give a X-ray view here. This is a coffee mug. A coffee mug is homeomorphic to a donut, the surface of a donut, at least. Well, yeah, we'll say a solid donut, because the material in the cup is solid, presumably. So yeah, these two are homeomorphic, meaning you can smoothly deform one into the other. The first thing you would do is imagine your mug is made out of clay, and either flatten this cylindrical part or like try to pull the bottom of your mug up so it's just a solid cylinder, and then gradually shrink the cylinder or expand the handle so that the handle actually becomes a donut, right? And so those two spaces are homeomorphic, partly because, yeah, they both have one hole, the hole where you hold it. A lot of people think the place where you put the water or the coffee or whatever is a hole, but not according to topologists. For topologists, a hole has to go all the way through. So if it doesn't, you can just undo it, right? You can extrude that hole back up and it's no longer a hole. So yeah, they both have one hole. That's at least one potential indicator that they might be homeomorphic, but you could actually define a continuous map with a continuous inverse that transforms one into the other. And there are lots of animations of this online that you could find. All right, so that's continuous maps and homeomorphisms. Those tell you a ton about what you want to know about your topological spaces. Thanks for watching.